Hi, I'm Drew. Today I'll be presenting an experiment that tests the viability of Raman spectroscopy in the search for life on Mars. So, I want to be an astrophysicist, and one of the biggest questions we face is, are we alone? Is there other life in our solar system? And this experiment gets us one step closer to having the tools and knowledge we need to answer that question. So, what is Raman spectroscopy? Well, it's a rapid and non-destructive technique well suited for the identification of organic biosignatures on Earth. But it's expected that the Martian environment will affect the stability and detectability of biosignatures. UV radiation, ionizing radiation, and oxidizing compounds could all destroy detectable traces anywhere from a few centimeters to meters of depth into the Martian surface. So the big question this experiment is trying to answer is, will Raman spectroscopy be effective in detecting biosignatures on Mars? Because we know it's effective on Earth. So currently we have two rovers that will utilize Raman spectroscopy. Perseverance, which landed in February 2021, and Rosalind Franklin, which has had its launch delayed to 2028 after the ESA and NASA stopped collaboration with Russia post the start of the Ukraine war. So to test the potential of Raman spectroscopy to detect biosignatures on Mars, we have to leave Earth. We can't replicate Mars-like conditions on Earth very well. So we are utilizing the ISS. So 7 biomolecules were mixed with Martian soil/rock and exposed to Mars-like conditions in low Earth orbit using the ISS. So for 469 days, these experiments were exposed to solar and galactic cosmic radiation, extreme temperature cycles, space vacuum, a Mars-like atmosphere, and two different groups were exposed to UV radiation and not exposed to UV radiation. So, what were the results of this experiment? Well, it turns out UV exposure largely reduces the detectability by Raman spectroscopy of biosignatures. Even the most resistant samples, chlorophyllin and quercetin, had their detectability drop by 30 to 50%. These results demonstrate that within a few years, biosignals on the surface of Mars would become undetectable. On the other hand, samples shielded from UV radiation showed remarkable signal preservation, with chlorophyllin and quercetin detection close to the control samples that never left Earth, despite being exposed to extreme temperature cycles, Mars-like atmosphere, and ionizing radiation. So these results support the idea that Raman spectroscopy is vital to the search for life on Mars, especially in the UV-shielded subsurface. And Rosalind Franklin will be equipped with a 2-meter drill to search for these biosignals. Future experiments would like to test a larger range of biomolecules besides just the 7 and start building a systematic Raman biosignature database that could prove a valuable reference for future missions searching for life on Mars and in the rest of our solar system. So to summarize, Raman spectroscopy can be a vital tool in our search for life. But the big question is it effective outside of Earth? So of the 7 tested biomolecules in this experiment, only 3 could be detected in the UV exposed samples. When samples were shielded from UV radiation, all 7 biomolecules were detected. This shows that when searching for life on Mars, we need to look below the surface. Biosignals on the first few centimeters of the surface are going to be hard to detect, almost impossible, and we need to search deeper. Now, my question for you is, I would like you to consider the results of the experiment and the high exposure to UV radiation on the Martian surface. How do you think this could affect the conclusions we can draw from the results of past experiments searching for life on Mars, such as those performed by the Viking landers.